Welcome back. See, I'm going to apologize in advance here for this. There's a lot of stuff here, so this is probably going to take 2 videos to get through. But a lot of stuff here, lots of good information that we will use kind of continuing on. And then make sure to pay attention here to the explanation and make sure you know why. So not only do we need to know the trends, but we also need to know why. So we can apply it to our periodic table, to a set of elements. Tell me, how these trends, which is going to be most reactive or which is bigger, and then why. All right, so periodic trends. Based on the way our periodic table is set up, there's this kind of repeating pattern of properties that shows up, this trend in data, and this is this sometimes referred to as the periodic law, but we're going to talk about 5 different periodic trends as we go along here. All right, the first one, atomic radius or atomic size. So first off, this is how it's calculated. So usually you just stick 2 atoms next to each other, a diatomic atom. In this case, like H2 is pretty easy to do, and you measure the distance from nucleus to nucleus and then divide it in half to get the radius of one of them. Not exactly the most accurate, but definitely easiest. So measured in picometers, that 10 to the negative 12th, if you remember that from our unit conversions. So atomic radius, just definition, half the distance between the 2 nuclei of atoms of the same element. Overall trend, so your atomic radius increases as we go left and down. So our biggest elements are down here, alkali metals. So francium should be our largest, with up here it should be helium as our smallest. All right, so why? As we go down a group, notice what happens. We keep adding those orbitals, and that's something I tried to point out during your activity with valence electrons. So moving down a group, atomic size increases since there are more layers of electrons. Look at lithium versus sodium. We go from 2 to 3, or 2 to 3, and then we go up 1 more to 4 for potassium. Pretty easy to see, I think. The other one then, as you move across a period, so look at element 7 and element 8, nitrogen to oxygen. As you move across, atomic size decreases. And you can't really see that from the picture, but if we think about what's happening, so electrons added to the same ring, so that electron is the 7th electron is the same distance as the 8th. But as we do that, we are adding more positive. So this one maybe has, fix this here. Needs to write where I want it to. All right, so this one has 7 positive charges. This one has 8. It has more pull to pull those 8 electrons in. That ends up winning out. Yes, it does add an 8th electron, but that 8th proton does win. Same thing for phosphorus versus sulfur. We have, if we count 1, 2, 3, 4, 5 valence electrons here. Sulfur has 6, so we've added that extra one, but we've also added that extra proton. So a bigger positive charge here versus there. Overall, here your periodic table, smallest element, definitely helium. Notice it doesn't have a 7th period on this. Really, those are they're unreactive. They're very reactive. So reactive that a lot of times they aren't found in nature. They're unstable sometimes. That's why we don't see that 7th period, but you can see the trend build. Francium would definitely be our biggest. All right, so review of ions. Atom or group of atoms with the charge. Here we're just going to talk about atoms. Gaining an electron results in a negative, which we call anion. Losing an electron results in a positive, called a cation. So here's our chart, sodium atom, 11 and 11. The ion lost that electron, so it has a positive charge, so more positive than negative. So the sodium would be a 1+. So ionization energy. Energy needed to remove that electron from sodium in this case, or whatever you are talking about. And it's always the most loosely held one. It's going to be easiest to remove one electron, or the first one. Increasingly difficult to remove the second or a third or a fourth. So focus here on the overall trend, because it is going to be kind of up and down. So as I said, going to be easiest to up and down, but what you notice is that lithium, sodium, potassium, if you look at kind of that trend of the 1A of the alkali, it decreases as we go down. So ionization energy, here's where it's weird. Increasing it, so where it's hardest to pull an electron from is how we are looking at it here. So ionization energy needed to remove an atom's most loosely held one. So yes, it's easiest to remove the first one, and then it's easiest to remove an electron from, like here on our periodic table, hardest from up here from helium. So why? Larger atoms, in larger atoms the electrons are further away. So we look at potassium here. This electron right here, further away from the nucleus than this one. So this one's 4 levels out, this one's 3 levels out, this one even closer, 2 levels out to get there. So it takes less energy because there is less pull. So lithium versus sodium, and then I didn't put a picture for lithium versus neon, but we'll talk about that here. Oh, maybe not. So lithium versus neon. Think about lithium. 2 rings, nucleus here. Lithium looks like this, 3 electrons. You go over to neon, so positive nucleus. That second ring with its 1, 2, 3, 4, 5, 6, 7, with its 8 electrons, also has 8 protons here in the nucleus, where lithium only has 1 proton. So this guy, same distance, so this one, same distance from this one, but 1 proton versus 8 holding him in, it's going to be harder to pull this guy out because of that greater attraction towards that more positive. Again, opposites attract. That's going to be a continuing theme throughout this part here. So overall trend, so overall trend, as we go across, it increases, like we saw there from lithium to, lithium to neon, and then increasing as you go up as well, like we saw with sodium to lithium. Ionic size. So another thing we can do is when we remove that electron or add that electron, how does this change the size? So positive ions, cations, are smaller than the atoms they form because of a couple of reasons. So if we just look lithium versus its charge, think about what happened to lithium here. It lost an electron. We got potassium here down below, so again, it gets smaller. Cations are smaller. Let's look at that. So potassium, it's 1 electron here out in the 4th ring. Well, if it loses that 1 electron, we basically erased this outer ring. It's gone. It's no longer there. So just overall visual looks smaller down here where we have 3 rings or 3 shells. You basically you eliminated a shell. It got smaller. Think about trying to give you an analogy here. You know, you're wearing your winter coat, you look pretty big. Take off your winter coat, you just automatically look smaller because of that. So when electrons are lost, remaining electrons are pulled more tightly. So that's something we didn't even talk about. Potassium has its 19 protons here, still has its 19 protons here, but it's now versus 18 electrons. So there's even some extra pull from the nucleus now. So instead of sharing 19 and 19 like you see over here it's 19 versus 18. Well, proton pull is definitely going to win there. So they're actually smaller than you would even expect from losing that ring. So if the outer layer of electrons is completely emptied, like what we saw here, not all the time is it completely emptied. This is just a case where we can definitely see that the atom gets much smaller. So you lose the ring and you have that extra pull. For the opposite, negative ions, so anions are larger than their atoms because this time we're doing the opposite. So we have 17 protons versus 18 electrons. For the chlorine -1, we have, oh, I messed that up. We have 17 versus, got ahead of myself, 17 versus 17. Over here, we've gained that extra. We have a -1 charge, so 18 protons. Screw that up again. I'll get it right. 17 protons versus 18 electrons. Well, electrons winning the battle there. Not enough pull from our protons to hold them tight anymore. So they've expanded now. So more electrons than protons, so each is held a little more loosely. So here, now you're trying to share this 17 positive versus 18. You know, think about, we got a class of 17 and we only bought one pizza, versus, you know, here we got a class of 18, we got one pizza. You're going to get a little smaller piece of that pie. And here, just a visual: oxygen versus its side versus its ion. Where, you know, these guys actually gain 2, so bigger. Fluorine versus its ion, again, just not enough positive to hold them in there. I'm going to stop this. Make sure you watch part 2 as well to get the rest of these.